When you're using the system, it shuts off what the motor normally did and it takes over. So it's a different power system and not a power adder.
So what's the big deal with the compressed air?
There is no energy consumed, or there are no parasitic losses from the vehicle. Energy or power it takes to compress the air is all done with the tanks outside of the car. So essentially you're getting something for nothing, as opposed to the supercharger. You've got the mechanical losses coming straight off the drive of the snout of the crank or whatever, and the efficiency of the blower. And with a turbocharger using exhaust energy, you're creating back pressure in the system, which decreases the amount of airflow through it. So I mean, you don't get something for nothing with any of those power adders, and with this you do.
Compared to nitrous then?
Nitrous is dangerous stuff.
Is it?
Hello.
This system doesn't care what size engine you put it on. It'll flow the same amount of air on a 500 cubic inch engine as it will on a 2-liter and make the same power.
So how much horsepower do you make?
The engine on its own will make 400, a little bit more horsepower. It's a 350 Chevy, 6,000 RPM motor, 9-to-1 compression, hydraulic roller. With 8 pounds of boost or so, it's over 800 horsepower. It makes about 50 horsepower for every pound of boost.
So when and where can I buy it?
This dual system should be capable of 2,000 horsepower, give or take, maybe a little more, I don't know.
I might have to drive it. This is our boost control unit that we've developed over a 10-year period. The person that developed it happens to be standing here.
Hi.
Rocket car.
My schooling or education was aerospace engineering, focusing on fluid mechanics.
You said earlier there's no timing change or...
Correct. There's been no change in fuel quality required or in engine tune.
Well, we designed our test car to be as simple as possible.
It's kind of hassle-free for the driver.
Yeah, once it's in, and two, it's a no-brainer. I mean, you go up to the starting line, you open the cylinders, you flip a toggle switch, and you mash the throttle, and away you go. That's all there is to it. When fully charged, these are at about 3,300 psi or 220 bar. Somewhat similar to a nitrous solenoid, only much bigger. The orifice in this is 1.5 inches in diameter. Air starts flowing from the line through the butterfly valve, and the butterfly valve is moved or articulated to maintain boost in the intake manifold via the boost controller.
Everything that we're using now had to be made for our system. It wasn't anything off the shelf that we could use, so it's been a long haul.
When did you start?
We started in 2002.
What was the most difficult part? Or are you in it now?
Yes. The car, the best it ever ran, normally aspirated, is like 1270. With 4 pounds of boost, the car ran 1080 or something. Cars run a best of 980 at 8 pounds of boost with a 370 gear in it. It picks up about 1/4 of a second for every pound of boost. Literally, you can outpower any other type of device. There's no magic in it, it's just the physics behind it.
But did you visualize the goal? Did you know it was possible?
Yeah, physically possible. You can draw this on the back of a napkin in 5 minutes. The idea is simple. It is very hard to make work correctly. Tuning this, tweaking that, changing this, doing this. Oh, this is important, that's not. The bottom line is, when you throttle high pressure air or low pressure, you get a huge temperature drop with it. So that's the big kicker here, is when you go from 3,300 down to 100, the temperature out of that regulator before it comes through the line can be as low as 200 degrees below zero Fahrenheit. And out of the ejector, we've measured 80 below zero. There's a phenomenon that commonly referred to as the Joule-Thomson effect, because that was the guys that discovered it 200 years ago or whatever.